everyone, welcome to the SWAYAM NPTEL course on mechanical and electrical systems of mining machines. So today is the 17th lecture on internal combustion engine, where we will be completing the remaining theory part that is left in this topic, and then we will be going to the tutorial problems. This lecture is a part of module 1, that is fundamentals of mechanical systems in mining machines. So in last class we covered the 4-stroke internal combustion engine, that is we covered the thermodynamic cycle and the different processes that are involved in both petrol and diesel engine. We also understood why a diesel engine is used in heavy machineries and heavy vehicles, and why petrol engine is suitable for light four-wheeler vehicles. However, for completeness of this topic, I'll be also covering the 2-stroke internal combustion engine, which we generally see in the two-wheeler vehicles that we ride. Then we will be going to 3 tutorial problems on this topic. Well, when we talk about a 4-stroke engine, as we understood, there are 4 processes that are involved, that is the intake, compression, expansion and exhaust. Our expansion process is a power stroke. Now the same 4 processes also happens in a 2-stroke engine. However, what is the difference? The difference is in 2-stroke engine, 2 process happens simultaneously. So what do we understand from this? In 2 revolutions of the crankshaft, we were getting 1 power stroke in a 4-stroke engine. However, in 1 revolution of the crankshaft, we will be getting 1 power stroke in a 2-stroke engine. So what does it means? The power output for the same engine will be doubled at the same speed, that is compared to a 4-stroke engine. Now, as we have understood who invented the Otto engine, that is Nicholas Otto, and who invented the diesel engine, that is Rudolf Diesel. So same way, we should also know who invented a 2-stroke engine. So the picture that you are seeing here is of a scientist named Dugald Clark, who invented this 2-stroke engine in 1878. Well, first the 4-stroke engine was developed, where all the 4 processes were specified in a sequential manner. The process was well established, and thereafter this 4-stroke engine was converted to a 2-stroke engine. So what is this 2-stroke engine and how can we achieve it? We will be understanding it in a while. But what important point that we should be noting from this slide is, for the same output power of a 4-stroke engine, we will be getting double power in a 2-stroke engine. Now in a 2-stroke engine, we should first understand how does the engine looks like. So this is a single cylinder of a 2-stroke engine, in which you can see the same way as in 4-stroke, there is a cylinder, there is a piston, there is a pin which we tell it as a gudgeon pin, and then there is a connecting rod, there is a crank pin, there is a crank, and then there is a crankshaft. This is similar to a 4-stroke engine. But what is the difference here? We do not have valves here. We do not have inlet valve or exhaust valve. Instead, we have 2 ports here. One is a spring-loaded inlet valve. It is also like a port, but it is a spring-loaded. There is a spring which is attached here, so which helps in opening of this inlet valve. So that is why we call it as a valve. And then there is a port here. There is just an opening which helps in taking away the burnt out gases out of the combustion chamber. Now one of the most important thing that you would see here is a deflector, which you will not find in a 4-stroke engine. So like your 4-stroke engine, so generally when you see a 2-stroke engine, it is a petrol engine. We hardly find any 2-stroke engine with diesel as the fuel. So that is why we have a spark plug here, which helps in the smooth combustion of the air fuel mixture that is taken into this 2-stroke engine. So that is why we need a spark plug to ignite the air fuel mixture. Now first of all, let us understand what are the what is how the process goes on. So we understand that this is the deflector, this is the spark plug, this is the cylinder, then this is the piston, connecting rod, crank and crankshaft. Here there is another component which we call it as the crank case, which covers or holds your connecting rod and the crank. So from bottom of this piston, the component that are encased in a case is called as a crank case. Here along with the spring loaded inlet valve and the exhaust port, we have another port which we call it as a transfer port. So through this the air that comes into the crankcase gets transferred into the cylinder, that is the combustion chamber. So let us first try to understand how the processes happen. Let me first write all the 4 processes: intake, compression, expansion and exhaust. So expansion is the power stroke. So let us first understand how the process starts. So this through this spring loaded inlet valve, the air plus fuel mixture enters into the crank case. So now the piston is moving from, so let us see the piston movement and the processes. Piston movement and the processes that happens. So my piston is moving from BDC to TDC. So here my intake or suction stroke happens. Suction stroke happens. Then again, when my piston has moved from BDC to TDC, my intake or suction stroke is taking place. Now my piston moves from TDC to BDC. Let us understand one by one and then I will show you how in one stroke 2 processes are happening. So first let us understand how it starts and then how simultaneously 2 processes happens. I will be explaining you in a while. Now from when the piston moves from TDC to BDC, that is top dead center to the bottom dead center, my transfer port opens. Transfer port opens and my combustion chamber or the air plus fuel mixture gets into the cylinder, right. So then my third process, again what will happen is my piston will move from BDC to TDC. In this process, my air fuel mixture gets compressed. Air fuel mixture gets compressed. So my compression stroke is happening. Compression stroke. Then number 4, from when the compression stroke happens, at the end of the compression stroke, when the piston reaches the top dead center, compressing the air fuel mixture, my spark plug, so in between, spark plug ignites the air fuel mixture. So now, due to this ignition, the combustion process takes place and my piston moves from top dead center to bottom dead center, giving me the power stroke or the expansion stroke. Now, when my piston is moving from top dead center to the bottom dead center, all my gases, unburnt gases, they will move out. In the same process, when my piston is moving from top dead center to the bottom dead center, in the same process, the burnt out gases, they will be exhausted through the exhaust port. They will move out of the cylinder through this exhaust port. But how do we see that there are two processes that are happening simultaneously? Let me make you understand again. Now here you see that when my piston is moving from bottom dead center to the top dead center, the suction stroke has taken place. Now when my piston is moving from top dead center to the bottom dead center, my transfer port opens and my air fuel mixture enters into the cylinder. Now in the third process, when again my piston moves from bottom dead center to top dead center, my compression stroke is happening. But at the same time, step 3, when my compression is happening, at the same time my step 1 is also happening, that is the suction of the fresh air fuel mixture is also taking place. So the compression is happening, at the same time my air fuel mixture is also getting into the crankcase. Now my step 4, that is the expansion stroke, expansion or power stroke is happening. My step 2 is also happening. In my step 2 is what is happening? My transfer port is opening, transfer port opens and the fresh air fuel mixture moves into the cylinder. So at the same time, when the fresh air fuel mixture is moving into the cylinder, my step 5 is also happening. That is, this fresh air fuel mixture is pushing out, this is the fresh one, is pushing out the burnt out gases out of the exhaust port. So that is why a deflector is given, so that when the transfer port opens, this fresh air fuel mixture does not move out of the cylinder through this exhaust port. It would move up in such a way that it would scavenge out the burnt out gases from the exhaust port. As you can see here, this process is called scavenging, where the fresh air fuel mixture moves from the crankcase to the transfer port into the combustion chamber, where it pushes out the burnt out gases. So many times it also happens that this fresh air fuel mixture, if the deflector is not designed properly, the fresh air fuel mixture may also move out of this exhaust port. So that is why the role of deflector plays a very important role in a two-stroke engine. So I hope you all have understood how in 2 revolution of the crankshaft we are getting 1 power stroke. That is, for the same capacity of a cylinder we are getting double the power as we would have got in a 4-stroke engine. So this ends the 2-stroke engine. Now let us see the comparison between a 4-stroke engine and a 2-stroke engine. So what we summarized from this study is the thermodynamic cycle that happens in a 4-stroke engine gets completed in 4-stroke of the piston, or that is the 2 revolution of the crankshaft. So therefore there is 1 power stroke in every 2 revolution of the crankshaft. However, if we see the same thermodynamic cycle in a 2-stroke engine, it has 2 strokes of the piston in which the thermodynamic cycle gets completed, or we can say that only 1 revolution of the crankshaft, all the thermodynamic cycle gets completed. So that gives us 1 power stroke for every revolution of the crankshaft. Now in 4-stroke, because of this thermodynamic cycle that gets completed in 4 strokes of the piston, the turning moment diagram is not so uniform, and hence heavier flywheel is needed. So let me first make you understand, when this piston cylinder arrangement they produce this power in the power stroke, there is a crankshaft, and at the end of the crankshaft there is a heavy mass which we call it as a flywheel. So this is in 3D, I am trying to show you it in 2D. So from this engine the energy gets stored in the flywheel. Now as I mentioned that there are 3 unproductive strokes in a 4-stroke engine, and there is only 1 productive stroke in a 4-stroke engine. However, in 2-stroke engine there are 1 unproductive stroke and 1 productive stroke, because there are 2 strokes in which all the processes gets completed. Now how do we see that this turning moment is not so uniform in a 4-stroke engine? So what do we understand this turning moment? It is energy versus time, in which we have, let's say this is the suction stroke, then we have a compression stroke where our energy is taken from the system. However, in a power stroke we get lot of huge amount of power that is seen in the turning moment diagram, and then we have another unproductive stroke, that is the exhaust stroke. So the maximum energy is taken herein, followed by suction, and then in exhaust. However, you will see a smooth turning moment diagram in a 2-stroke engine, and hence it has a lighter flywheel which can be used for a 2-stroke engine, unlike your 4-stroke engine where the requirement of a heavier flywheel is needed. Again, because of 1 power stroke for 2 revolution, power produced for the same size of the engine is less, and for the same power the engine is heavier and bulkier. However, in 2-stroke engine we have 1 power stroke for every revolution, so the power produced for same size of the engine is twice, and hence for the same power the engine is lighter and more compact. So because of 1 power in 2 revolution, lesser cooling and lubrication is required, because in every 2 revolutions we are only getting 1 power stroke, that is combustion is happening in 2 revolutions. So lesser cooling and lubrication is required, so lower rate of wear and tear. However, we do not see the same in a 2-stroke engine. In 4-stroke engine we have valves, that is the inlet valve and exhaust valve. However, in a 2-stroke engine we do not have any valves, we have ports. Now, in a 4-stroke engine, it is comparatively higher weight and complicated valve mechanism. The initial cost of the engine is more. However, here due to lighter weight and simplicity, because there are only ports, so the initial cost of the engine is less. Here, higher volumetric efficiency is obtained due to more time for mixture intake. Here, since the time duration for mixture intake is less, so lower volumetric efficiency is attained. In 4-stroke engine, the thermal efficiency is higher, part load efficiency is better. However, in a 2-stroke engine, thermal efficiency is lower and part load efficiency is poor. We see the 4-stroke engines in cars, buses, trucks, tractors, in industrial engines, aeroplanes and so on. However, in 2-stroke engine, because it is low cost, compactness and lightweight as well, so that is why we see it in mopeds, scooters, motorcycles, etc. So with this we end the theory part. Now we come to the numerical analysis of the energy that we get from an engine. So what we understand is a engine takes the fuel energy and convert it into mechanical energy. So it converts the chemical energy to mechanical energy. So the total energy that the engine receives is it gets it from the mass of the fuel and the calorific value of the fuel, like what kind of fuel is being used, whether it is a petrol, diesel or any other fuel. So the energy of the fuel comes from that. Now while it is taken into this system, so there are certain losses that happens while it is taken into the system, which happens due to exhaust or coolant or radiation while the combustion process takes place. So the total energy minus your losses, that is the energy losses due to exhaust, coolant or radiation, we call it as indicated energy or net work. Now during the process takes place, while the combustion takes place, there are also some other losses due to friction, pumping, or there are certain unaccounted losses as well. So if we subtract that from the indicated energy, we get the net energy, that we call it as the brake power, which helps in the mechanical work, and that is stored in the flywheel. So we get two energies, one is the indicated power and one is the brake power, and the losses that are incurred due to exhaust, coolant, radiation and what so not, we call that as a friction power. Now when we try to understand this system, so what happens, there is air and fuel into the engine system. This is the engine system boundary, and then there is exhaust. So there is the chemical energy that is given in here, and here we get there are certain losses that happens at the system boundary or at the exhaust, and at the end what do we get? We get the work output, so which we call it as the brake power. Now there are certain efficiencies of this system, so which we call it as the indicative thermal efficiency or brake thermal efficiency or the mechanical efficiency of the engine. So now let's say we get an energy from the fuel that is dependent on the mass and calorific value of the fuel. From that, when we deduct the energy that is lost due to exhaust, coolant or radiation, we get the indicated power, and from that when we reduce down the energy losses in friction or pumping, we get the brake power. So how do we define the indicative thermal efficiency? It is the indicative power divided by the total energy. Now this total energy is equal to mass multiplied with the calorific value of the fuel. Now the same way, how do we get the brake thermal efficiency? It is the brake power divided by the energy that is utilized, that is given to the system by the fuel. And there is something called as the mechanical efficiency as well, which helps in driving the mechanical components of the system after the losses that are incurred while the fuel is taken into the system and it is taken out of the system. The burnt out gases is taken out of the system. So if we talk about this mechanical power, mechanical efficiency, that is given by the brake power divided by the indicated power. So here there are certain things that I would like to discuss more about it. So now here your mechanical efficiency is equal to brake power by, what is this indicated power? This is brake power plus frictional power. So what do we understand? My frictional power is nothing but indicated power minus brake power. There is also something called as the mean effective pressure that exists inside this system while the gases are taken in. So that we denote it as PIM, which is the indicated mean effective pressure of the engine. So how do we define it? We define it as IP is equal to PIM LANK by 60 into 1000. So here your indicated mean effective pressure PIM is equal to 60,000 multiplied by IP by LANK. So here my L is the length of the stroke, A is the piston area, N is the number of power strokes. So what do we take it as? We take it as N for 2 stroke. Let's say that is 1 for 2 strokes. So let's say there are multiple number of revolutions. So how many number of power stroke happens in each revolution? And it is taken as N by 2 for 4 stroke, because in every 2 stroke we get only 1 power stroke. And K is the number of cylinders. Now there is also something called as PBM, which is the brake mean effective pressure, which is given by 60,000 multiplied with brake power divided by LANK. So with this we can get this effective pressures that prevails inside the cylinder of an engine. Now coming to the tutorial problem, So the first question tells the cubic capacity of a 4-stroke over square spark ignition engine is 245 cc. The over square ratio is 1.1 and the clearance volume is 27.2 cc. So now we have to calculate the bore, the stroke and the compression ratio of the engine. So if we see the solution of this problem, so my Vs, that is the cubic capacity of my engine, will be equal to pi by 4 d square L. So here, since it is a over square engine, so my d will be greater than L. So how much my d is greater than L? It is greater than by 1.1. So d is equal to 1.1 L. So here my L is d by 1.1. So here we can write, in place of L we can put it as d cube by 1.1. So which is equal to 245 cc. So if we find dq is equal to 343, so my bore diameter d is equal to 7 centimeter, my stroke length L is equal to 7 divided by 1.1, which is equal to 6.36 centimeter, and the compression ratio R is equal to Vs plus Vc by Vc, which is equal to 245 plus 27.2. So here my clearance volume Vc is given as 27.2 cc divided by Vc, that is 27.2, which is equal to 10. So the compression ratio of this over square spark ignition engine is 10. Now coming to question number 2. So my question number 2 tells that the mechanical efficiency of a single cylinder 4-stroke engine is 80%. So what is given in the question? My Nm is given, that is Bp by Ip is given as 0.8, that is 80%. The frictional power is estimated to be, Fp is given as 25 kilowatt, that is Ip minus Bp is equal to 25 kilowatt. So this I can write as my Bp is equal to 0.8 times of Ip, which is equal to 0.2 Ip is equal to 25. So my Ip comes out to be 25 by 0.2, which is equal to 125 kilowatt. This is one answer. As the question tells, calculate the indicated power and brake power developed by the engine. So the indicated power we got as 125 kilowatt. Now how do we find the brake power? We just subtract it. Brake power is Ip minus 25, so it is 100 kilowatt. So this is the indicated power and brake power of this single cylinder 4-stroke engine. Now coming to the third question. So the third question tells that we have to find out the speed at which a 4-cylinder engine using a natural gas can develop a brake power of 50 kilowatt working under the following conditions. So what are the conditions? The air to gas ratio is 9:1. Now the calorific value of the fuel is 34 megajoule per meter cube and the compression ratio is 10:1. So, the volumetric efficiency is given as 70% and the indicated thermal efficiency is given as 35% and the mechanical efficiency is given as 80% and the total volume of the engine is given as 2 liters, which is equal to, we can tell it as 2000 cc. Now, how do we go ahead with the solution? What we have to find? We have to find the speed. So, how do we find the speed? So, what is K? K here is 4. Now, my brake power is given as 50 kilowatt. My air to fuel ratio is given as 9:1. Calorific value is given as 34 megajoule per meter cube. Compression ratio is given as 10. My volumetric efficiency is given as 0.7. Indicated thermal efficiency is given as 0.35. Mechanical efficiency is given as 0.8 and the total volume is given as, total volume of engine for a 4 cylinder is given as 2000 cc. So, here what do we see, that the total volume of engine is 2000 cc. So, the total volume of each cylinder will be 2000 divided by 4, which is equal to 500 cc. Now, then we find the swept volume. So, how do we find the swept volume? So, here we should know what is the percentage of swept volume in this single cylinder, where the compression ratio is given as 10. So, what do we know? The compression ratio is 1 plus Vs by Vc. So, here Vs by Vc is equal to 10 minus 1 is 9. So, my Vs is 9 times of Vc. So, let us say the total volume is 10. So, my swept volume will be 9 by 10th of the total volume. So, my swept volume will be 9 by 10 times of the total volume, that is 500, which is given as 315 cc. Now, we have to find what is the volume of the gas that is taken in a cycle. So, how do we find the gas? So, here my air fuel ratio is 9:1. So, if I need to find what would be my gas percentage, so I have to divide this swept volume by 9 times, so that I get what would be the volume of the gas that is taken in. So, the total volume of air fuel mixture is taken as 10. So, if I have to find how much is my amount of gas which is taken in it, so it is 315 by 9, which is given as 35 cc. Now, when I know my mass of the fuel, so the energy of the fuel, I can very well find out energy of the fuel in each cylinder, which is equal to my mass. If I convert it into meter cube, this 35 into 10 to the power minus 6 multiplied by the calorific value here, which is 34 into 10 to the power 6, which gives me around 11 90 joule, which is equal to 1.19 kilojoule. So now what I know is my indicated thermal efficiency NITH is equal to IP by energy that is supplied, energy supplied to each cylinder, energy supplied per cylinder per second. So this is equal to my so what I can find out is my energy that is supplied, energy supplied to each cylinder will be equal to, the thermal efficiency is given as 0.35 and my IP will be equal to my brake power by my mechanical efficiency. So brake power is 50 into 10 to the power 3 divided by mechanical efficiency 0.8 divided by the indicated thermal efficiency 0.35, but that is for the engine. So multiplied by 4, so which we will be getting, so we divide this whole value with 4, so we will be getting energy supplied to each cylinder or energy supplied per cylinder, which is equal to 44.64 kilojoule. Now the energy supplied, now the energy supplied per cylinder, this is energy supplied to each cylinder per second. So energy supplied per cylinder in kilojoule is equal to E1 by N by 120. So which is equal to 44.64 into 120 by N, which is equal to 5356.8 N. So here we have found the energy of the fuel in each cylinder as 1.19 kilojoule. So which energy supplied per cylinder in kilojoule, which we have found as 53.56.8 by N, which should be equal to 1.19 kilojoule. So which implies my N will be equal to 4500 RPM. So this gives me the speed at which my cylinder is using a natural gas and which would be developing a brake power of 50 kilowatt. So the speed of my engine would be 4500 RPM. I hope you understood this problem. You can follow more such problems in this book of by V. Ganeshan of internal combustion engine. Thank you. We will be continuing with the next topic, that is the power transmission in any automobile or any heavy machineries in the next class. Till then, have a good day.